All right, projectile motion, which is otherwise known as nonlinear motion. So we've been studying linear motion, motion going either directly across the floor or straight up and down. So either straight horizontal or straight vertical. This time we're going to look at motion that looks more like this. All right, so that parabolic, we kind of introed it with hang time. So the parabolic motion to figure out this distance. Now we're going to focus, so this was from chapter 4, figuring out this distance. Now we're going to be talking about figuring out this distance and velocities. So the title is Projectile or Nonlinear Motion. This should be in Cornell Notes style. This is your title. It's chapter 5. And then all your headings or topics go here. Topic number 1, vector quantities. This goes in the topics section. Okay, we know this. This is very repetitive, so I'm going to move quickly. Write this down quickly. This is a quantity such as force. It has both magnitude and direction. All right? This is velocity. This is acceleration. This force in general. This is newtons. Okay. Scalar quantities, another header. This has to do with mass. There's no direction for mass. There just is. Mass is. It exists. Volume, that's how much a liquid takes up. So if I have a volume of water, it's just a number. There's no direction to the water. It just is. And then time. There's no direction to time. All right, this popped up on chapter 4 test. Somebody asked me a question about it. Time has no direction. It's a scalar quantity. It has no direction. I've said that like 3 times. Hopefully you got that down. Pause if you didn't. I'm moving quickly. Okay, velocity vectors. A vector, an arrow whose length represents the magnitude of a quantity. So the length of the arrow tells you the magnitude. And direction, the way it's pointing is the direction. So this small magnitude, it's a northeast direction. This large magnitude, bigger than this one here, and it goes in the southeast direction. That is not a strikeout. This is still important. So when you draw a velocity vector, okay, keep in mind this is velocity vectors. Okay, if you didn't title it, this is important. Velocity and force vectors are different. Force represents usually a stationary object, all right? You're sitting in your chair. There's a force vector going downwards representing gravity, all right? That's your weight in newtons. And then there's the normal force vector, which is pushing up from the chair. So if you're sitting, that's a force vector, okay? Those forces of you sitting in the chair, of gravity pulling you down and the chair pushing you up, normal force, that's force. This is velocity. They're going to be represented a little differently. Okay, so let's talk about those comparisons. A force vector deals with magnitude and direction again, but this is an applied force. Okay, so you might want to add that like as a miniature header under velocity vectors, or you could do this as a header, as a topic, and then do this as a subheader. Magnitude and direction. So this is the same story I was telling you. There's support, or normal, and then there's gravitational force, okay? And that's usually of a stationary object. You can do it for a rolling ball as well, which we're going to see in the second one. Okay, so remember when we said velocity, the force vectors of a ball moving at a constant velocity. So remember, if this ball is moving at 1 meter a second, all right, in this ideal frictionless world, there's no force actually being applied. So you wouldn't, the only force vectors you would draw is force of gravity and force of normal. That's it. Okay, those are force vectors. Velocity vectors. A velocity is representative of the speed, not the force. So now we negate gravity, and we ignore gravity, and we ignore normal force. This time, this is the 1 meter per second. And notice each arrow is the same, saying this is a constant velocity. It's continually moving 1 meter per second to the right. So please, 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 this is a subheading, realize that velocity and force vectors are very different things. Don't get them confused. They have different measurements. So units on a velocity vector is usually meters per second. I'm going to go back for a sec. This is newtons. Okay? Keep that in mind. Unit, newtons, unit, meters per second. Okay. This is not acceleration. Okay? If there was an object that was accelerating, meaning a force was being applied, the velocity would not be constant. So this is an acceleration. You would have a little arrow, and then the velocity is getting faster, and then the velocity is getting even faster. All right, this would be like you flooring it to get on the highway. Okay, each velocity is increasing. So this is acceleration, this is constant velocity, these two. Okay, so velocity vectors, you know this. Resultants is the sum of the vectors. So in this case, we just did random, like pushing and pulling experiments. This time we're dealing with, instead of forces, we're dealing with velocities. Okay, so if this airplane was moving with the wind, the airplane is moving at 120 kilometers an hour, but it has a tailwind. Oh, hang on, I misread that. Well, we can do it that way. It has a tailwind of 20 kilometers an hour. The resultant would be 140. This, I misread it, so pardon me for that. It actually states that the plane itself is going 10 kilometers an hour, and it has a tailwind of 20 kilometers an hour. So its total speed we add is 120. Okay, what if the plane is going 100 kilometers an hour still, but it's getting a headwind? The headwind is head-on, slowing you down. You'll feel this when you're driving in your car. If it's really windy and you're hitting a lot of air, you're going to notice that you're going to have a harder time maintaining the constant 100 kilometers an hour. So instead, the plane is actually traveling at 80 kilometers an hour. So this applies for velocity and force, but now we talked about velocity, you know what it is. This is why direction plays a role, because it matters if you have a tailwind or a headwind. Okay? That's where we're going to start really getting into the plane stuff too. That's how the resultant works. Okay. Now, we also learn this as well. We learn this for forces. If a 3 Newton force is applied upwards and a 4 Newton force is applied to the right, what is the resultant? And this time we use A squared equals B squared plus C squared. It's back. I told you, a lot of this whole learning experience is it spirals. We keep coming back to things. So this time we're using velocity. If a plane is moving, or a car is moving north, or a cart is moving north at 3 kilometers an hour, but there's a wind blowing at 4 kilometers an hour, how is that going to push you off course? Same thing, a boat, you're paddling at 3 kilometers an hour across a river, but the river is flowing at 4 kilometers this direction. Okay, here's your river. All right, if you're trying to row across the river, you're going to end up moving at this angle. Okay, and you can use Pythagorean theorem to determine at what speed you are actually traveling. Okay, component. Another major vocab word. If I haven't pointed this out, this is the heading. Put it over there. Components of vectors. This is a heading, put it over there. What is a component? We talked about a resultant. Now a component are the two pieces of something moving in a weird direction. So if you're a pitcher, or even if you're shooting a basketball, so it's basketball season right now, when I'm recording this, you shoot a basketball, right? It goes up, and you hits the net, right? You swish it right in the net. Beautiful three-pointer. It's amazing. Crowd goes wild. Woo! Nice shot. Winning game. You won the game. Whatever. Okay. This is a projectile. The basketball is a projectile. All right. There are two components to this. There's the horizontal component because it's moving horizontally towards the basket, and there's a vertical component. All right. Meaning it's going to go up and come down, and this is a component that gravity affects. Okay, so often they're often mutually perpendicular, like you see in my picture, and the sum is the resultant. Okay, so it's usually a combination of two or more components. We are only going to deal with in two components, because once you get more components, it gets crazy, and that's upper level physics. So same story here. This is the boat story. Here's our boat. He's trying to cross the river. The river's flowing in this direction, and it's pushing it off course. So if you start at position A, how fast will you be going to get to position B? And this is where you use. So the resolution is the process of solving this. So this is C. Sorry, we'll do this. That's A, and this is B. Okay? A squared, B squared, you're going from this point to this point you can solve using A squared plus B squared equals C squared. I feel like I wrote that wrong back here. Yeah, A squared plus B squared equals C squared. Sorry about that. I mean, ultimately, it works out. It comes out in the wash here, but as long as you pay attention to what components. But I apologize for that. I'm trying to move quickly. Okay, so again, you need parallelogram rule. Okay, this and this is parallel. This one and this one, they're parallel and the same length. This is the one you all had problems with on the test. This is hard. Parallel, parallel. Get a ruler. The second one, easy. Okay, there's your resultant. Second one's easy. They're actually perpendicular lines with a right angle in each corner. This is a rectangle. Okay, which makes that resultant a lot easier. Okay, we're stopping there. There's some work in your textbook that you need to work on after these notes. On the back page of these notes or the next page of these notes, you need to complete the homework on this page. All right? Homework will be posted on Canvas. Pay attention.